Okay, so welcome to day 4. We know what we've looked at so far. What we did yesterday was we talked about 8-bit processors and the move between 8-bit and 32-bit processors and various modern hardware platforms. Now this is my ideal model of the world. So people rejoice at the fact that their organization has moved from 8-bit to 32-bit processors because it makes it easier for them to apply TTC schedulers and similar architectures in their systems. In reality, what many organizations do is they do something like this. At last, we've got rid of those 8-bit processors. Now we can get rid of that TTC scheduler and run a full RTOS or Linux in the system. The point of this session is to suggest that this kind of move, using a conventional real-time operating system or using Linux, is something to approach with care, because life gets much more complicated in any system in which the tasks can interrupt one another. So in any system which supports task preemption, life becomes significantly more challenging. And what we're really going to focus on in the first part of today is why that's the case and some of the challenges that result from task preemption. We're going to look at solutions to that. We'll break for coffee, tea, and then we'll come back and we'll look at some aspects of distributed systems and the use of CAN to create systems that involve multiple processors communicating over a serial communication bus. So our goal today is, broadly, how can you run more than one task at the same time? And that's essentially the focus of what we're doing. So we've looked at this problem before. If I have these two sets of tasks and I want to run them simultaneously, and I have a processor with a single CPU, then I face a number of challenges. And we talked about the fact that sometimes you can find a design solution to that which allows you to keep the design tidy, clean, and easy to maintain, and still match a single processor. That's not always the case, though. Overall, I'd argue that where you can, you should use a TTC approach in your systems. Lower overheads, great predictability, ease of certification for these kind of systems. In a nutshell, advantages of this approach. Now, with appropriate design approaches, such as the one we looked at on the previous slide, you can sometimes reduce the number of systems which require task preemption, require tasks to interrupt one another, but you can rarely avoid it completely. So how do we manage to make that work effectively? We're going to consider full event-triggered multitasking designs, time-triggered hybrid schedulers, and working with multiple processors in distributed systems. So, what are some of the challenges involved in working in this area? Let's do the basics first. So this, if you like, is our system input. This is the task set we want to run, and these are the tasks. These are the tasks we want to run. We've got a single processor. These now indicate the task priorities in the system. So low priority, medium priority, and high priority tasks. So in this design, what we would expect to happen is something similar to that shown on the bottom line in practice. The medium priority task starts running. It's preempted by the higher priority task. There are no tasks of higher priority than that, so that task runs to completion. Then the medium priority task completes its execution, then the lowest priority task runs. So that's what we would expect to happen in a simple design, and that's sometimes what people assume will always happen in their real-time operating system. But there are some significant complications. Let's just consider that these are our sets of tasks. And these are roughly the the priorities of the task. So A has highest priority, E has lowest priority. Now, assume there are some shared resources. So assume that task C is using an analog to digital converter, and task A is then ready to run. So task A is a higher priority and is ready to run. If we go back a slide to here, that's like saying this task is using the analog to digital converter. And suppose it's using the analog to digital converter here. And suppose that the high priority task also needs to use the analog to digital converter. What happens? Suppose this task, suppose it's not an ADC, suppose it's just an array of data that you're writing to. This task could be halfway through writing to that array of data. Then the higher priority task could interrupt. So the data is only half updated, some old, some new, and this task requires access to these data, and it uses data that may mean absolutely nothing and may be positively dangerous. What would you do in those circumstances?
Write data fully first.
Okay, so essentially that's all you can do, is to try and ensure if this task is accessing a shared resource, and that's the concept here, if there's a component or data or something that's shared between these two tasks, then if this task is in the middle of using such a resource and a higher priority task wants to interrupt, so what is the effect then going to be here? So your suggestion is that this task is right into an array and we have to let this task finish.
The high priority task doesn't actually start execution at the required time base.
So it doesn't. So all we can do is effectively have the high priority task wait until the writing operation on that array is complete, and then the high priority task can run. That's a challenge. And that effect is known as priority inversion. Because what's happening here is the low priority task has, because of the shared resources, it's effectively being treated as if it has higher priority. So because it's using a resource down here, and because we can't deal with a situation where the resource is half used when something else has, when the access to that resource is incomplete when another task interrupts, we have to let that resource access complete, which means that implicitly this task is being given for some time a higher priority than you've originally allocated to it. And it's an effect known as priority inversion.
Would it not be the case always rather than just temporarily? Would the priorities get inverted for the whole time?
Probably not, but we'll look at that a little bit later on. What you would do is probably temporarily change it. I mean, well, suppose there are two shared resources in the system, and they share two different shared resources. Yeah. Then what we've decided to do is give this one the higher priority all the time. But then we just repeat the problem later on in the execution when it comes to the second shared resource, when this, which is now the medium priority task, would be blocking the new high priority task. So you can only do it temporarily in most non-trivial systems. So this assumes that the tasks don't have shared resources. In practice, when the tasks do have shared resources, life becomes a little bit more interesting. Now, sometimes what you can do is, what people sometimes do in a system is, if there are tasks that may interrupt, well, give me another solution another potential solution to this that might avoid these conflicts between A, B, and C and the ADC. So we're having problems because these three tasks are sharing a resource. Give me one potential way of addressing that.
Give them all their own resource.
Okay, so we could have three ADCs. Yep. Let's not give me another solution that doesn't increase the hardware count.
Do tasks in blocks. Do the conversion for one first, and then the other. And then
Okay, so what are you doing to my diagram here? And one way of doing that would be to say, what I've said here is, task A might use channel 1 on the ADC, task B might use channel 2 on the ADC, and task C uses channel 3, whatever. Suppose we just give task A responsibility for the ADC, and we don't let any other task access the ADC. Does that solve the problem?
well, if tasks B and C are called from
No, so task B and C will still be called by the scheduler. If they're called from A, they're just part of A. If not, why not?
how do B and C function without the actual data from the ADC?
I didn't say they didn't have the data. They don't have direct access to the ADC.
Okay, so do they indirectly take data from A?
So
via
A could pass data to the shared data area, and then B and C could access it. But the problem then is, we've taken away that shared resource and we just replaced it with this one. And that's essentially what happens. If you're going to have communication between the tasks, that implies some kind of shared resource. That's
Reading that surely doesn't matter, because they're not changing our schedule. Like, A is the only one that can change it, but the other one's going and reading. Surely that's
well, so when, what happens when A is writing to the data?
You can't B and C can't access it while it's still written. So
Yep.
afterwards they can access.
So the processes can become short, but anytime, and you may manage to do that, agreed. If there's, you could control it so only one place is writing, others are reading, that will reduce the complexity of the calculations, and sometimes you can do that for the whole system. But you will still have situations in which these tasks, we're assuming here, these tasks, we don't know the times at which these tasks are going to execute. So it's not a time-triggered system, and in effect, the timing here, they could run almost any time. The blockage due to the ADC may itself be very short. An ADC conversion's a couple of microseconds. So even if you were blocked, it might be only for a couple of microseconds. But a couple of microseconds might be enough to disrupt the behavior of your system overall in a manner that was difficult for you to handle. Let's take it forward a couple of steps. If we're going to have any kind of shared resource, we need some mechanism. The first basic issue here, what would be the issues if we had no protection around the ADC? What might happen in the ADC if this task was using it, and then this task interrupted? What do you think might?
mid like conversion or something like that, and you could get some horrific data back.
Yeah. So this one could have configured it to read from channel 2, say. So it's configured the ADC and it's about to do a conversion. Then it's interrupted by A. A sets up the ADC to read from channel 1, does its conversion because it's higher priority, and then returns and then leaves the ADC again, completes. Then this one runs, and this one basically has set up channel 2, set the ADC to start converting, then it's been interrupted. But it doesn't know it has been interrupted. So as far as it's concerned, it's now back in it's just continued in the same state that it was in before, And typically what that will be is it'll be waiting for an ADC conversion on channel 2, but meantime, the ADC converter has been reset to do a different operation and is no longer has any knowledge of the configuration that was previously used for channel 2. So this thing will basically wait forever for an ADC to conversion to complete that won't happen. You'll pick that up in your timeout loop, and you can avoid some problems potentially with that if you're lucky. You can pick it up in your timeout loop, but you won't get the right data back from the ADC. So what we need to do is we use some semaphores or mutexes, which we're not going to discuss here, but locking mechanisms to basically say that this guy locks the ADC and says nobody else can use it by now because I'm accessing it, and that's effectively what would cause the blocking of task A when it tried to execute and access the ADC. So we can solve those. There are simple locks and there are mutexes, which are locking mechanisms that are associated with a particular task. These are not without their complexities. There's a module in this program on real-time operating systems which covers all of these bits and how to implement them in much more detail. We're not going to do that today. So we talked about the fact that what results from this, what can result from this, is a period of priority inversion in your system. Let's just look at that in just slightly more detail and take it on to the next level and look at solutions to this. So this might be what we want to happen in a system. We have two tasks, a low priority task running, accessing our ADC. We have our high priority task running like this. And what we would ideally expect to happen in practice is this task to run for 2 units, this task to click in for 3 units, this task to finish off for 2 units. Yep. You ignore these areas which are called critical sections, which are the times at which you access a shared resource. If you ignore those components, that's what we'd expect to happen. In practice, we get something like this, where the low priority task runs for 2 units. Because it's using the ADC, and the ADC has been locked now, the high priority task can still run briefly, because in the first part of the high priority task, it's not a critical section. It's not yet using the ADC, and this comes to your point from earlier. So we don't need to block it at that stage. But then we get to the high priority task needing the ADC. It cannot do that because it's locked. So the system switches back to the low priority task, lets that run, and this is the high priority task is then blocked for that interval. This is a period of priority inversion. Once the low priority task is finished with the ADC, we switch back, run the high priority task to completion, and then we run the last part of the low priority task. For a start, we've got all of these things happen. What are these? What are these called? It's called a context switch when you switch between running one task and the other. What would you have to do in these circumstances? If you've not met it before, what would you have to do?
Making the switch or ensuring that the switch doesn't affect the system?
To make the switch, what is required in order for me to be able to run the low priority task, run the high priority task, and then switch back to the low priority task? What am I?
You'd have to make sure it knows what it's got to do and where it needs to go back to.
Yep. So essentially, we've got to store the state, the current state of this task, which typically means stack contents of some kind, where we are in that task, what the return address is, values of any local variables, etc. All have to be stored. And they have to be stored somewhere in memory. That process is going to take time. So, and it's going to require memory. Imagine there are 50 layers of tasks here, which is not uncommon. There are 50 layers of tasks. Suddenly, you're starting to talk about quite a lot of memory and potentially really quite a significant amount of time getting these data into and out of memory in a manner that's quite difficult. Often, timing is quite difficult to predict. So this is a simple case of priority inversion. With two tasks, if you had to, you could probably predict the timing behavior here reasonably closely in these circumstances. So we could work out how long the critical sections were, we could work out where they were in the code, we could do our best to estimate the timing. Let's make one small change to this. So now I've added in, same example as before. So we're still with this one, but what I've done is I've added in another task of medium priority into this system. So now we run the low priority task for a chunk. The high priority task kicks in, then the low priority task, but then it gets to the point where the low priority task is accessing our critical resource again. We've not got all of the way through using that critical resource when this medium priority task is due to run. There are no critical sections in this medium priority task. So there's no reason why that task cannot interrupt this one. So why shouldn't it? The logic is that it should. So this one doesn't access this. Well, the medium priority task doesn't need to use the ADC. So the ADC is locked out, which means that the high priority task has to switch out and give control of the CPU back to the low priority task. But then, unfortunately, a medium priority task comes along. Now it's all normal code, no critical sections. So there's no reason why it should not interrupt the low priority task. That's the logic. Now then what's happened is we've got really serious priority inversion problems happening in this design. Because this is unbounded. This could be any duration at all depending on, and typical task levels, OSs might have a couple of hundred possible levels of tasks. They won't have a couple of hundred tasks running probably, maybe 50 tasks running in a typical system. Suppose you have half a dozen tasks in here of different durations, potentially with their own sets of critical sections that they're fighting over through this, and they can interrupt this kind of behavior. In any practical sense, it's impossible to pick up this behavior. If you had diagrams like this, it'd be okay. I spent yesterday afternoon, while you people were sweating over exercise, I was speaking to an automotive company yesterday afternoon that's having significant reliability problems. They couldn't even tell me what the processor load was on their system, not even approximately. They didn't know whether it was 50%, 90%, or anything. They didn't even know that. They had no way of picking up any of these details. They just didn't have any way of providing that kind of information. And the reason they had me there, with half the company around the table, was basically because the stuff is just no longer reliable. Used to be okay, now it's got a bit more complicated, and this is the kind of thing that happens. We need an extra little bit of functionality. System X is working. Let's add another little task. Bingo. But the problem is, very, very difficult to predict what the impact of even one tiny change in the task set here is. Yeah.
Why can you not have like an interrupt that picks up the fact that the high one's still going and kicks back in, so it doesn't run the meeting? Why would that not make sense? Why would it? Oh yeah, it does. But I mean, the high one's still going. Why does it not say, "Hey, I've still got a high one going"? I know it hasn't kicked in and like said this.
But it can't. But the next part of the high priority one cannot run, because to run it needs access. So the critical resource lasts for 2 blocks here. So the challenge here is that we've not finished that critical section, not finished access to that critical section when the medium priority task kicks in, and that's when the nightmare starts.
Does that also mean that you get your like shutdown function or whatever if that runs for too long?
That's so essentially by this point you're starting to look at task guardians, watchdogs, other disaster recovery mechanisms. But as we talked about yesterday, it's very likely this will just happen again.
Is it not just simple to use another microprocessor? Like multiprocessor in line?
Let's take the automotive industry again as an example. They are notorious for keeping bottles of champagne in the fridge. They can save one resistor on a PCB in a they're going to create 2 million of these cars. They can save one resistor. They get the champagne out. Everybody has a glass of champagne. Because the margins are very, very tight. If you go out and they say, yeah, we can solve your problems, all you need are 2 more microcontrollers in the thing, they'll just laugh you out of the place. So you say, but it's only a $1 processor. They say it's not a $1 processor. It's got to go in a box. It's got to be wired in. It's got to have the external circuitry, etc. on it. It's going to cost us $10 a vehicle. Said our margins are probably $30 a vehicle. So, yeah. So it's just not possible. So they want to squeeze all of this into the single design, which is where this all came from in the first place. So that's scenario we get into. Just quickly, this is again touching on your point from earlier. This is what happens if you've got 2 critical sections. You can guess the behavior. You end up with one task waiting for one to release, the other one waiting for the other one to release, and you get a situation which is catastrophic. It's known as deadlock because you have 2 tasks each waiting for the other one to release. It's like, yeah, any game of cat and mouse or something like that. Now this is how we can solve these problems. Let's go back, and again, you've actually solved this for me earlier. So we can address this, and we address this by saying, okay, while this task has access to that critical resource, we'll give it, let's take the simplest model first, we'll give this maximum priority when it's accessing that critical resource. And in that case, what happens is this will run till the end of the critical section at maximum priority before this comes in. So this one will be displaced back to start only after this has completed, and then everything will run quite happily. The same thing will happen here. So we'll not have this lockup here. We'll instead give this higher priority than this one. This lot will run through, and then everything else will run as per required. So this would run first to the end of the critical section, then the high priority task would run, then the medium priority task would run. That's okay. Yep. Let's just take it back to this. So these tasks can run at any time, and that's the highest priority task. Which task would you make the one, if you had a task that had to take time-critical data from this ADC for your control application, and we're back at your 1 microsecond or so temporal resolution, which task do you make the you make the time-critical task the highest priority one or the lowest priority one? Obviously, you make it the highest. And often then what people do is they assume that because it's the highest priority task, that means it can do the time-critical operations without any difficulty. The polite response to that is rubbish, because it can't. And you see what happens with that. Even here, well, let's just stick with the one that's probably comprehensible. Even here, if that was the high priority task requiring access to that resource, and it requires access to that resource at time 3, when does it get access to that resource if we change the task priorities dynamically?
5.
It's going to be 5, yeah. It's going to be too late. 2 ticks too late, 2 segments too late. And that's just in a simple system with 2 layers of task priority. So the challenge is, we've got a challenge here, which is we don't want priority inversion. So we want to make sure that tasks run according to their priorities. How do we, and we're addressing that problem here by doing what? Well, one way of viewing this is to solve the problem of priority inversion, we invert the task priorities. And there is no other way, really, of describing what's going on here, because that's exactly what you do. To avoid the problems of priority inversion, you invert the task priorities. We've devised, over the years, the world has devised, you would not believe how many papers, etc., have been written, research papers, research projects. Many people spend years of their life looking at ways of addressing this problem, because it's a significant issue. And we've evolved a scheme which says, okay, if we want to promote this task in priority, we call them priority ceiling protocols. What priority does this task need to take on? Suppose there are lots of different resources shared in this system. How do you determine, when you've got shared resources, how do you determine what priority this task needs to have?
You need to look at where it does the existing.
Well, how could you determine, does this task need to have, in this setup, does it need to have infinitely high priority?
Might do, like it's in a car and it's a brake pedal or something, you want it quite
Well, to avoid that, to avoid the clash here, all it needs to have is a priority equal to that, so that it can run. And it needs to have a priority equal to that, because it needs to have a priority equal to the priority of the highest priority of any task which accesses that critical section.
Is that not just artificially changing the priority?
I grant you completely, it is. But if you do that, you can avoid that's what you have to avoid. So the scenario, if you don't do it, is catastrophic. So we put locking mechanisms in to avoid interrupting the ADC when it's halfway through its operation. We can deal with that. And we give the task priorities, but if we don't use some form of ceiling protocol to change the task priorities dynamically during the run, then we will get this scenario. So our option is to dynamically change the priorities during the run in a controlled way, which avoids this kind of scenario. But it's challenging. Let me just take you forward a couple of examples. So we said, effectively, even if you make your time-sensitive tasks have highest priority, you've still got a challenge here. This is a nice one. NASA, 1997. Mars Pathfinder. They used a real-time operating system. They had a priority inversion problem. Now, the good news is that they had a team of great people. They were able to devote that team full-time for 3 weeks to analyze that small system on that Mars rover, and after 3 weeks, they identified the problem. And after 3 days, they managed to download a correct solution to that problem. 3 days after they identified the problem, they downloaded a complete solution to that Mars rover. So that is good. But if that was an A380 flying around the planet, you don't have the luxury of 3 weeks to solve these problems. You need to solve the problems quickly. And there are very, very few organizations that have the luxury of a team like NASA's main software team to spend 3 weeks assessing any system. Remember, this is not just the prototype. This is the one that's gone through all of the NASA-grade testing before it's been sent anywhere near a spacecraft. And they still have priority inversion problems. It's not a mammoth system. It's just a little semi-autonomous rover that works its way around a few rocks on a planet. And they still get significant priority inversion problems. So the problems are real. It's simply because getting your head around the possible combinations, take a non-trivial set of tasks, give them some shared resources, try and work out what the possible timing behavior is, and you're in a scenario where I would argue you can very rarely comprehensively test that system. You can only test as much as you're able to do so, but you can't ever provide any kind of proof that the system's going to operate correctly. Let me take you back a chunk, because some of you are still looking skeptical here. The world rarely works like this. What I've done here is I've said, these are nice little chunks of critical sections, and they're exactly one time period long. In reality, that's probably 35 microseconds long. this time. Next time it runs, it's probably 45. And next time, maybe 13.5. So even if I run it 1,000 times or 1,000,000 times, I've probably got combinations of different durations of these task sets, which it's only when I'm 7 miles above the ground, in a particular set of weather conditions, with a particular vibration input or whatever else, that suddenly I'll discover this particular combination of requirements which causes my system to have difficulty. And that's the challenge we face. That's what we can't afford to have happen.
Are there tactics like, if you use the interrupts only to gather the data, but then schedule a task to run?
I have a solution. I have a solution for you. So let's take another look at this. Suppose you've got a time trigger design. You know when the tasks are going to access the resources. So even if there's tasks interrupting one another, you know when the tasks are going to access the resources. Let's just go back. We can stick with this diagram. Suppose this is time triggered. Suppose this setup is time triggered. The challenge we've been looking at here is we've said, okay, maybe C is using our analog to digital converter. And then B comes along, it has a higher priority, and it's blocked. So that's the origin of the problems we have. Suppose it's time triggered, this system, and rerun that scenario again. Here, C doesn't just grab that resource. That would be rude. Instead, what C does in a time-triggered system is C says to the scheduler, I need to access the ADC resource now. The scheduler says, I'm afraid that's not going to be possible because task A requires that resource in 2.5 microseconds, and it will take you 3.5 microseconds to access the resource. Please put yourself to sleep. That's a fundamental and profound difference between the systems. So in a time-triggered design, the conflicts don't happen. That is not priority inversion. That's correct task priorities. And it only happens because we know, even if we're allowing the tasks to interrupt one another, which we haven't done in the designs we've looked at up until now, even if we allow the tasks to interrupt one another, you get much better predictability from a time-triggered system. And that's the reason why, because you don't have a task preemption issue. Most of the time, many times, you can actually statically design the system so that you are pretty sure in advance that these conflicts won't happen. Then at runtime, you check. So before a low priority task accesses a resource, it checks with the schedule and just double checks to make sure that it does have time to access that resource. If not, it suspends and ensures that the high priority task that's doing your data sampling, which must be done with a 0.1 microseconds, etc. time constraint, that will happen. And you can guarantee, absolutely guarantee, that that will happen. That's the difference.
Doesn't this just make sense?
Sorry?
Doesn't this just make sense? Like if you can like have like a scheduler running like at priority levels and everything like that, doesn't it just make sense to do that anyway?
I think it's a sensible way to build systems, but it's not the way that a lot of people do. A lot of people would hook these up. What happens is these tasks might be linked to a serial interrupt, a CAN interrupt, a timer interrupt, various forms of interrupt which happen at non-deterministic times. And if that's how your system has been constructed, then you cannot, there's no way for you to say, you don't know when A is going to run next. So B cannot say to ask the scheduler what's happening next because the scheduler doesn't know. That depends on the outside world, and you're back in the scenario where essentially the environment is in control of your system. Essentially, you've handed over control of your software to the interrupt system. And therefore, you've handed it over to the outside world, and you have no control over exactly what is going to be running when in the design. It's not cost-free. It's difficult to design these things from the start. And that's the price you pay. To put that together as an event-triggered system is comparatively easy. That's why people like it. And it allows you into false sense of security. You get that system built really quite quickly. The challenge is, I would argue, you will never ever get it tested if it's non-trivial. If your system uses about 20% of the CPU resources, you've got a small number of interrupts, typically around about 20 tasks or less in your system, you can probably make this work in an event-triggered design. If you have something of greater than about 20 tasks on the average, as a rule of thumb, it becomes a practical impossibility in most systems to ever iron out the possible combinations of conflicts and constraints you have here. Many systems run at 90% plus loading. They just don't have spare capacity for error. It's back down to the cost issue again. If it was running at 20%, they'd have used a smaller processor. So they tend to get them back up and running at about 90%, because that looks like a cost-effective solution. You've got very little headroom to deal with any errors in these circumstances. So that's one of the differences between some of these designs. So this is where we'd argue that TT architectures effectively are a bit like MISRA C. They're a subset of what goes on here. So these guys, this world has lots of interrupts enabled. In a time-triggered system, you only have a very small number of interrupts enabled in the design. And we've got somebody doing a PhD, been doing this for the last 4 years now, modeling some of these things. This is what we think of as the verification effort. This is the system size. Think of that as tasks. Round about here, we think the number's about 20 tasks. 15 to 30 tasks, somewhere around about 20 tasks in here. And the overall cost of building a TT design, verifying it, doesn't go up very steeply. It's cheaper and simpler to build a small event-triggered design, because you just have to hook up a few interrupts. As you gradually build this thing up, the verification effort for these event-triggered systems then goes through the roof. Happy to argue this through. There's plenty of MSc projects in this area. Anybody wants to explore some of these points. So if you want, this is my brief summary of the different worlds. Conventional real-time operating system, it's a model like this. New manager joins an organization, and standard thing is, my door is always open. Got a problem? Just come in. Don't even bother to knock. You've got a problem, just come in, plonk yourself down, stay for as long as you like, tell me your problem. It's easy to build that system, looks very friendly, but it's very difficult to predict how the behavior is going to go. What's actually probably going to happen is you're going to burn out your new manager within about the space of about 3 weeks, and the system's not going to work in that way. A time-triggered system, by contrast, is different. You go and knock on the door, the manager just growls and says, you make an appointment with my secretary, you don't come in here. It's boring. No open door policy. You get an appointment with the CPU 3 minutes, 4 seconds, whatever, from now. That appointment is for 15 microseconds. And when if you exceed that time, the task guardians got rid of you like that. And you're replaced with a different task and you never appear again. And you're automatically replaced with a backup task for that because you have done something wrong. Once you've got this, if I take a group of people out onto a runway, there are 2 planes out there. One of them is time-triggered, one of them is event-triggered. I say, which one do you want to fly in? And the people will say, okay, without doubt, I want to fly the time-triggered one. Both planes have passed all the tests. People will choose to fly the time-triggered one. Take them all off the plane again. Say, okay, strip all the software off the plane. Get the same group of engineers onto the runway and say, right, we've got 2 planes here. Before you go on holiday, you have to build the software for those 2 planes. One of them's going to be event-triggered, one of them's going to be time-triggered. And some smart chap at the back put his hand up and say, do I have to fly the final result? You say, no. You say, well, I want to build the event-triggered one because I'll get on holiday more quickly, but I don't want to fly. We'll go and have a holiday in Blackpool and we'll come back when they finish building the time-triggered one because that's the one that we're going to go and fly. And that's basically the way the world works. They're difficult to build. This is not scalable as a general rule because you can't tell what the impact will be You've got 51 tasks. What's going to happen when you add task 52? Very difficult to predict exactly what that is. Here, it is scalable. We know exactly what the slots are in the schedule. We can tell you in advance whether you can add task 52 to this. We can tell you whether it's going to fit in or not. That's essentially where I think the world fits together. Let's look at one simple implementation example. Let's not look at any of these bits. Let's, in fact, start with this.
You said the NASA thing had a problem.
Yeah.
Have there been any planes that have had problems?
Nope, but almost all planes are built using TT architectures.
Like for them, is it more appropriate just to shove another processor and say that's going to work?
But they won't have to do it. Essentially, the problems I was running through at the beginning are problems related to using a single CPU with a conventional preempting real-time operating system. I don't work with any aerospace companies that would contemplate doing that. So the problem, that particular problem wouldn't arise. There are organizations which would do that. See, the Mars rover was not safety critical. Nobody was going to die. NASA got very embarrassed, but nobody died as a result of that process. So you could argue it wasn't an inappropriate design choice. It just caused them embarrassment. But for many, the downside of that is, let's suppose they were washing machines. And you are a well-respected washing machine manufacturer producing high-grade machines. What would you do in the circumstances if there were 3 million of those out in the field and you started picking up these problems? That's just it's a business loss that you really don't want to face. So that's why even those kind of organizations are now starting to say, hang on a minute, are we absolutely sure that this is actually going to work correctly after people have been using it for 3 years, after the drums got a little bit slower, the responses from that are coming back a little bit late? Is it actually still going to work as well as it works on the test bed now? Yeah, that's where we go to. Remember the scheduler update function from yesterday. This is scheduler update function for a new scheduler. Think about that for a minute. Let's go back to this. I've changed two things in this diagram. So it's a standard kind of tick diagram that I've shown you before. I'm afraid I don't know which page I'm now on. I've changed two things. Let's start with the simplest one from yesterday. Suppose that's task A, and this is a TTC scheduler, exactly what you were using yesterday. Is that a problem? We've said that you typically assume that the worst case execution time of any task is going to be less than the tick interval. Do you have to? Does it matter? What happens here? So the interrupt occurs, we increment a tick count. The interrupt occurs, we increment a tick count. And we just go back in each case. We do that briefly, very short period, we go back to running A. So we're keeping track of the time, but that's not a problem necessarily. It might give us a bit of disruption, small disruption to the timing behavior of A that we would need to be aware of. And we might decide in an ideal world that we want to run this on a piece of hardware that doesn't force us to have these ticks. So we could omit these and take into account tick and just go straight to the next one. So change the interval between the ticks, but we wouldn't have to. we could run with this simple model, and if we were willing to tolerate the level of jitter in these task timings that would result from these brief interruptions, we'd be fine. You comfortable with that? So let's do one more thing. Task X, function X, I'm going to call from the timer ISR. And I can do that too. Typically, I'll make this task very short. Kind of thing you might want to do with that, take a sample from your ADC. You need to do it more frequently, but this long task gets in the way. Why not just interrupt that task? Very briefly, we know the ADC sampling takes a couple of microseconds. So if we were to allow a 5 microsecond block, that would make much difference to the behavior to the overall load on the system, and we could comfortably take an ADC sample in the middle of this. We could do that, or suppose that task runs for a second, and we got an emergency stop button that we need to check every 50 milliseconds or something. Check the emergency stop button in this preempting task, and you'll make it run quite happily. That's what a time-triggered hybrid scheduler does. So it's a very simple way of introducing task preemption into your system. So we've now got the facility. If we do that for one task to interrupt another task, it's still time-triggered, but we've got an ability to support task preemption. This is a very powerful architecture. Very simple, very powerful. To create this, you need to take 2 lines of code, make a couple of lines of code changes to what we worked with yesterday. A couple of lines of code just to call, at the simplest, we just call one function from here. Stick with that for a minute. Suppose this is an ADC task, and I've got 0.01 microsecond requirement on my jitter in my ADC sample, which is not a million miles from possible reality. So I need to get the timing of that task really pretty precise. What's going to happen here compared with suppose we just ran a task X in a TTC scheduler like this. We'd expect very low levels of jitter. Why?
Run it at that time every single time.
Okay, and what state is the processor in here, here, and here? In our typical TTC design that we've used up until now.
The task count is at 0.
You're at a known state where you're guaranteed that that's what it's waiting for.
So what state is that? I think idle. Okay, and that's the key bit. So we're in idle mode here. Each time. We're in idle mode each time. What about the jitter here?
You're somewhere in a function somewhere.
Somewhere in a function. So we know here we're almost certainly in a different state each time. We know that we've got to complete the current instruction that's running before we can service the interrupt. So that's going to go on. So we're likely to have more jitter in that version than this version. Solve it.
Isn't it almost predictable though? Because no matter what, it's still only going to take an instruction to do it and then go to the...
But the instruction, sometimes, take a Pentium, instruction length variation is a factor of 10,000. Challenging. Let's make it 0. you can tell me how to make the jitter in that identical to the jitter in this.
Still using interrupts.
How do you do it?
Synchronize interrupting with tick, so that task X runs at every interrupt and the tick corresponds to that.
Well, that's exactly what happens here. So the
basically
interrupt.
You have to stop a bit before that. basically.
Okay, that's exactly what I want to do. Tell me how to do that.
Could you
Use a variable and call it to stop it before the time actually reaches the next tick.
So assume that we give you a little bit of flexibility here. When we say 1 interrupt per microcontroller, sometimes we cheat a bit. Suppose I let you use 2, but it still has to be a time-triggered system.
Use one interrupt to stop task A, and then at the
So,
next interrupt.
okay, so now we've got 2 interrupts. That's sounding good. So now we've got 1 interrupt that happens here, just before. Now what are you going to do?
put it into idle state?
Put it into idle. Okay, so this one puts it into idle mode. And the time here, we probably have to work out from the data sheet, or usually, because they don't usually give you enough data, you have to work it out practically, how long it takes the thing to get into idle mode. And you have to experiment a little bit, because it's going to essentially have to finish the current instruction, whatever that is, go into idle mode. Then the jitter in this will be the same as the jitter here. The cost is you've lost 0.5%, 0.25% or something of your available CPU time in the system. So you want to make that optional. Maybe you don't care. Maybe you don't need to get jitter levels in that case, in which case don't do it. If you do, you've got it as an option. And you've got it as an option because the system's time triggered. So you know when the next thing's going to happen, so you can get the system into a known state before you get there, and you've got control over the way the system operates. Let's just take you forward. So this is what happens, and these are some of the impacts. So we had somebody do a PhD in this area as well over a few years. This is an ARM7 microcontroller running a TTH scheduler in this form without the idle mode added in, without the second tick. And this is what the kind of jitter levels you're getting from, so it's not an 8051, it's quite a reasonable performance, 32-bit ARM7 based microcontroller running at what I think about 60 megahertz or something. Pretty fast device, and we're getting 0.8 microseconds of jitter from this task. In this particular implementation, the jitter level was reduced down below 0.1 microseconds by introducing this mechanism, EPAM. And that was sufficient for the great majority of applications. So just by including that additional idle mode component, we managed to reduce the jitter level down to an acceptable level in these applications. It's not detailed in here, but you can do the same thing with shared resources in just the way we talked about, where the system can ask about access to a shared resource. We call that a trap protocol, and you can do that, which reduces jitter further in situations where there are more complicated combinations of resources that you might be fighting.
Is it not possible to put that all into one interrupt? Like have the interrupt go first?
There are lots of variations on this. You can't quite though, because essentially what you want to do is you want to finish the current instruction, go into sleep mode or idle mode, and then you have to wake it up again.
Well, you could use knobs.
Then,
You know how long that
so what instruction would you? You'd have to do quite a lot of it really gets quite complicated.
But I mean, if your tick count was global,
Yeah.
you could just say wait until tick count, and then just starting it then, even though you're just knocking before that. Like while you know
Okay, so what instructions are you using to check whether the tick count is equal to 1 or not?
If it's equal to
But so you're going to go through a set of non-equivalent, so it can't be all NOPs because you've got some instructions that are checking the flag.
you can work that out, so you're going to know that how long that takes. It's going to be
Well,
every time.
so if you go through that, I mean, what you could do with this, you could say, well, this is just ridiculous, because essentially, why don't we just split this task up manually into these chunks, and then we don't need any preemption at all. Now you could do that. Now, if you have a look at the exercise we've set you today, we've set you that basically this is an exercise, and we've added the tweak in, which is representative of the real world. Suppose I give you a scenario here where I say I want to control. Suppose this is an ADC doing an FFT type task, which is not uncommon in digital signal processing type applications. ADC and fast Fourier transform. What we've said in the exercise is I want to vary. It might be a 256, it might be a 128 sample FFT, fair enough. But we've also said, oh, but yeah, I want to change the sample interval live. Then you're in trouble. So sometimes you can, and the really ideal way of building these is completely statically. Work out exactly when the task preemptions occur and do it statically, and do it manually like that, but it's enormously time consuming. And it has no flexibility. And you have to redo it again if you make changes. So you can sometimes do it. The advantage with this is it's a little bit more dynamic, and it doesn't require you to know in absolute perfect detail exactly. It doesn't require you to balance out the code all the way through the system every time. You can deal with a degree of dynamism in the system here, and you still get that very predictable timing behavior. So that's overall the advantage. In this case, we've set the exercise deliberately, which says, oh, and I want to change the ticket. And that is the nightmare scenario for any kind of static form, because it's then, all you could do then would be have a set of possible options in a lookup table, which would be well nigh impossible to do. So that's task preemption. You can do it safely. There are lots and lots of these systems running. Sometimes what people do is they run versions That's a very common form of simple hybrid scheduler. So that's running in our while one loop, and then we've got our interrupts every millisecond or something. Sometimes called a foreground background system, and there's a lot of arguments as which is the background, which is the foreground, but whatever. But that's a way of running this, and then this interrupts periodically. You can do some of these mechanisms here, but that's a simplified form of it, which can also be effective. So these bits are obviously not real time. If you insist they're soft real-time systems, and these just keep running, doing some basic processing, and this interrupts periodically without perfect control over timing, but it's pretty good. That's where we're going to pause briefly. And then we're going to look at systems with multiple CPUs just after coffee or a brief break. Okay, I think we're now running again. So, what we looked at first part of this morning was situations in which you want to run multiple tasks and you've got a single CPU. So you're reproducing, you're multitasking on a single CPU, typically running part of one task, pausing it, running the next task, etc. And as far as the user is concerned, it looks like a multitasking environment. Another option, which was raised a couple of times this morning, was why don't we use more CPUs? Sometimes that makes sense. Typical modern car has something like 50 plus processors built into it. Typically those are communicating using controller area network. We're going to look at how you can begin to put together systems with multiple CPUs in this session. And we'll do more with this in the case study tomorrow. So tomorrow you'll be working with distributed systems. In the exercise this afternoon, you'll be working with a single processor and multitasking systems. Multiprocessor designs cover a range of different areas: automotive, aerospace, medical, industrial automation, etc. You might have various units hooked together in a way. It makes it simpler in an automotive application, for example, to have one processor in each anti-lock braking system. The automotive company can buy different braking systems from different suppliers, can plug them all together onto the same bus. There are numerous advantages to this kind of design. It allows parallel processing. Spread the processor load, run long tasks and short, frequent tasks without preemption. Increases the number of peripherals available. Suppose you've got a compiler for an 8051 microcontroller. Suppose you need 100 I/O pins. What could you do? Compilers are expensive. Tool sets are expensive. Most of the time, you might work in application areas that only require a comparatively limited peripheral set. Suppose your 8051 only has one UART and you need two UARTs. Why not use two 8051s? Hook them together. Synchronize those two processors, do data transfers between them. You can use the same set of tools, and you can make the system work quite happily in that form. It might even give you increased reliability. Talk about some of those things. You might have some greater immunity to errors, etc. Suppose we've got an aerospace system. And the plane is turning. The rudder is hard over to the right. The various control surfaces are in different positions. And for whatever reason, the control between the cockpit and the tail of the aircraft is cut. So you lose control of the rear part of the plane. What you want to happen in those circumstances, well, what do you want to happen? What do I want to do to the control surfaces? No, I don't. Never be able to land the plane. I'm going hard right. So the rudder is hard over to the right. The plane is turning out of the climbing hard, turning out of the airport. The rudder at the rear is hard over to one side. The control surfaces are hard over a steep banked right turn, and I've lost control of some parts of the plane. What do I want to do to those control surfaces?
Do you want to reset them and then link back to normal so using another method?
I want to get the plane on the ground without killing anybody.
Give control back to the pilot thing, so like, what, can he still control?
He can't. He has no control over the rear part of the plane. So what do we want those rear control surfaces to do?
Something they can't. Like, you can't do them, surely. You can't control them.
Can't control them, but what's the best fail-silent position for the rudder on the aircraft? Straightforward. Okay. So if you make the system intelligent enough to know that it's lost control, lost connection, communication with the main part of the aircraft, then at least you can have your intelligent subsystems. If they're dumb and they're just told turn the rudder according to a particular angle and that's all they can do, you're in trouble. But if they're more intelligent, quote, intelligent, unquote, you cut the cabling, then you can set them up so that they automatically lost communication. Let's get into a fail-safe state, and then we've got a better chance of getting that plane onto the ground. If you lost control over all the control surfaces, and except for the engine, and you got all those control surfaces into a neutral position, you can still fly the plane. It's horrible. You can even control the direction by changing the engine speeds. You can get a degree of control by the way you speed it up and slow it down as the acceleration. You can do all of these things. It's horrible, but you can just about get that plane back on the ground. And you can just about control it with virtually any surface, as long as the ones that you're not using get themselves into the right situation. That's only going to happen if you've got some way of taking intelligent action in these circumstances. So, some of the key challenges. Suppose we've got multiple nodes. It's all about time. So suddenly our challenge comes, up until now we've been worried about this task running, synchronizing the activity of those tasks. What about multiple processors? We've got to keep the clocks on those processors synchronized in this design. we've got to be able to share data between the nodes. Sometimes what people do, they put a couple of nodes together. They put CAN connections. We'll talk about what CAN does, but it's essentially a serial communication protocol if you've not met it. And they just send messages between the nodes. When the messages arrive at a particular node, they generate an interrupt. And that's a common behavior. And we say, okay, have you thought about the timings at which you're transmitting the messages? No, it doesn't matter. We just let them, essentially, we let the messages fly around the bus. We make sure the bus is not overloaded, and we deal with the messages when they arrive. It's very difficult then. Then you've got a whole bundle of events happening at random times coming through that system, and it's difficult to predict what's happening. We need ways of synchronizing the clocks, sharing the data, and detecting and managing errors in this system. If we take these three processors from the same factory, we take these three oscillator modules from the same factory. They've been generated exactly the same time. We pick them out of the next compartments next to one another. When they've come off the conveyor belt at the end of the factory, we plug them onto the microcontrollers. We flash an LED on each microcontroller using exactly the same software. What will we see?
Visually, they might be similar, but naturally, there might be slight differences.
Start them all off at the same time, set them flashing, go back 2 days later. What will you notice? They're going to be different. Key factors that control, so even if you take them out of the box, run them at the same time, the frequencies will not be the same. You'll get drift between them. Take this kind of scenario. Portable traffic light controller. That one's controlling that end of the network, that one's controlling that end of the network. You've got roadworks. You only want the traffic to go that way. Not that way at the same time, single passageway. Put this together, put this one in high sun, this one in cloud. Don't synchronize the clocks. One of the key determinants as to how fast this oscillator will run is the temperature. And it's not even a nice simple relationship with temperature. It's a pretty horrible graph. But the temperature will have an impact on the oscillator frequency. So unless we've synchronized these in a sensible way, they're going to drift out and we're going to get car crashes in this kind of environment. Just one other factor with these things. Characteristics of a quartz crystal. Anything else you're familiar with on a day-to-day basis that has physical characteristics similar to quartz? Glass. Very similar. That's the brittleness, fragility. Take your quartz crystal, smash it on the table, it's likely to break. Take your quartz crystal, put it on your aircraft engine, shake it around for a few hours, you may well have problems. What do you do if it has to be heavily if the system's going to be subject to vibration or large physical shocks, etc. Are there alternatives?
Shield it from vibration, just like the CD drives are shielded.
Okay, so you shield it, and you can try and do that, and that adds to the costs. Or you can use something like an RC oscillator. Challenge with an RC oscillator is this looks temperature sensitive. It's nothing compared with something like a simple RC oscillator, which has massive drift in it. So it's more robust, but it gives you rise to massive drift. Swings and roundabouts. It's difficult. It may be possible for you to set up a network that has some more robust nodes in it if you've got a master node that has accurate timekeeping and it can keep track of the time on the rest of the network. There are various options to look at there, but it's not straightforward. These things themselves give rise to challenges. This is the most important slide in this session. We're going to take a set of nodes. We're going to hook them together on a bus. Some of you have seen some of this before, and you're back in familiar territory again. On the master node, we're going to drive the scheduler in just what we've done before. So we've got our timer driving the scheduler, generating periodic ticks, driving the scheduler on the master node. One interrupt per microcontroller. On the slave nodes here, they have a scheduler. The scheduler's driven by periodic interrupts. Those periodic interrupts come from here. Every time a tick is generated on the master, the first thing the timer ISR does is to send a message on the bus to all of the slaves on the bus. The arrival of those messages generates an interrupt on those nodes. And that interrupt drives the scheduler on those nodes. Very simple design, very simple way of synchronizing the activity here. So this generates periodic ticks. This sends messages. The arrival of these messages generate interrupts on these nodes, and these interrupts drive the scheduler on the node. So the scheduler is pretty much the same as you've seen before in sessions up until now, but the interrupt source, there's no timer running on these. The interrupt source is the CAN bus in this situation. Still one interrupt source per processor. We just use a different source to drive the scheduler in this case. Suppose, so how does this slave know that the bus has been cut?
As soon as it doesn't receive a tick, it can start at some time.
Okay, let's keep it one step at a time, please. Yep. So what does this know about the world? What does this know about the ticks? This is generating ticks every 10 milliseconds. This one expects ticks every 10 milliseconds. Okay? So every time this receives a tick, what could we do? I'm going to let you put a watchdog timer on each of these nodes. What would you do? So every time we get a tick on here, we set the watchdog to 11 milliseconds, say. Every time we get a tick, we refresh the watchdog. So provided the ticks keep coming, everything's fine. If we miss a tick because something's gone wrong with the bus, this will pick it up within 1 millisecond or however fine resolution you want to set it. So the watchdog overflows after 11 milliseconds. So within 1 millisecond of the expected time, this will know what's happened. And then we have two options. What we might do with this one, typically this one at the other end of the bus, is we might have this one wake up from a watchdog reset, listen to the bus. So I've woken up from a watchdog reset, that means something has gone wrong. Is there another master on the bus? Listen. Can't hear anybody. Okay, I'm now the boss. The king is dead, I'm now the king. Right, and I'm going to start sending ticks down here. Now it may be that these guys are still working, but the setup is broken here, and we've only got this half of the network. So it's not trivial. You're going to have to work out what the sensible behavior is in those circumstances. But if you want to do so, you have techniques here which can allow you to pick this system up and keep it flying. So we have a way of detecting errors. The tick messages give us a way of sending data between the master and the slave nodes. The master node also needs to know what's happening and also needs to be supported in data transfers. So we send data between the master and the slave using the tick messages. Look at those a little bit more. And we send acknowledgement messages back from the slaves to the master, also in the same tick. And the way that this happens in the simplest networks is there's a master tick from the timer. The master sends a tick message which goes to all slaves and triggers an interrupt on all slaves. Usually just one slave replies. And we just simply alternate between, we just go around the sequence in a round robin manner for all the slaves replying. Sometimes you have every slave replying to every tick. which would mean you have a tick here, tick message is sent, and every slave replies. The consequence of that is that the tick interval gets longer. In a CAN bus, which is a typical framework for this, the message lengths are about 150 microseconds, 0.15 milliseconds. The message length, typical message length, is about 0.115 milliseconds. So you start, so if you want to have 1 millisecond ticks in the system and a little bit of overhead, you're not going to manage to get every slave to reply in a typical environment, because it would simply take too long to have that happen. So there has to be some kind of compromise between the tick length and the message duration, and there's nothing we can do about that. There's a basic limitation depending on the baud rate of the bus we're using as to how fast we can transfer the data. So that you could find, if you're doing the MSc, you can gain access to all these online automatically. Otherwise, we can let you have copies if you want to see them. So we've done various bits with these kind of designs as well. So we've talked about some of the error handling here. The slaves can easily pick up if a tick message is not received because they know when to expect it. And the master also knows the schedule of the message transfers back from the slave to the master. So the master can also work out what if messages have gone missing or if damage has occurred to the bus in these circumstances. And these are some of the ways in which we can deal with errors. Typical, enter a safe state and shut down the network. It's the simplest thing you can do. You can set the network up so if the master fails or if the master detects a problem, the master simply shuts itself down, in which case the tick messages stop, the slaves get no tick messages, they themselves are reset and they go into fail silent mode. And that might be the best behavior for your particular system. We might need to restart the network. We might decide to restart the network and just assume it was a temporary failure and run from there. Or we can engage backup slaves or engage backup masters. There are various other possible combinations that we can run through. I think I've said this about use of watchdog timers to do this. Then there are some basic things we have to think about. We've got a system with 100 nodes. Each node is 99% reliable. If we need all of the nodes to work for the system to remain in effective operation, the overall system reliability is just 37%. 0.99 times 0.99 times 0.99, etc. gets you down to 37% quite quickly. So the general process of adding more components into the network simply gives you more things that can go wrong, and if you're not careful, they will simply reduce the overall reliability of your system. And there are various ways in which we can deal with this. Suppose this is our network. We can, and suppose we've got failing nodes, we can have the network fail and we can have nodes fail. We can have backup, we can add backup nodes to the system, backup master nodes, backup slave nodes. That gives us a means of dealing with particular failures of particular nodes. We can duplicate the CAN bus. This is particularly common as well. Run a separate CAN bus down each side of the vehicle, whatever it is. This is great fun. Possibilities of breaks in the bus at different points, in which case these individual nodes end up having to route messages in order to keep the system operating. That's a nightmare in software to implement, particularly if you're trying to do so while ensuring you've got precise timing behavior. It's challenging to get that to work. Let's just look at one more factor with this. That shows what happens if the network is cut. Suppose the network is shorted. If the network is shorted, in most cases, the whole bus becomes inoperative. So shorting that, if you cut it, that's comparatively straightforward. It's not good, but it's comparatively straightforward. If you short it, it's not that simple. I short it here and I short it here, I've lost the whole lot. What do I do? What's wrong with my basic network topology?
That is plus. Should be star.
Could be a star. Yeah, so I could configure this. So effectively, we've got some kind of configuration where the slaves are connected through their own buses to this system. It's pretty well as clear as mud. So this is bad because I've got a single point of failure, which is the bus. So this is good, right? So now I've got a single point of failure, that's the master. So that's not good either. What would you do with that? I need a second master, yeah, okay. So, sorry, that should be a master. And then we have to hook that onto all of these devices as well. And we can make that work. We can have this one generate messages, and these slaves echo those messages, so this master can work out whether everything else is connected to the bus, and this one can step in if particular problems occur. Challenge with this, that's got cheap wiring. This wiring gets more complicated and more expensive. It's all swings and roundabouts. But we can make any of the designs that we're going to talk about, we can make this work quite happily in the same kind of way where messages are sent over each individual arm of the star to the slaves, and that can trip the schedulers and the slaves. That works just the same way as it works when you're in a bus topology. There are other ways of synchronizing the nodes here. You don't need to synchronize them with every tick. You could synchronize them less frequently and let them run their own clocks in the gaps between it. That's another way of doing it. But then you run into scenarios of working out how frequently do you have to refresh them, what happens in errors, and what's your error recovery time in these circumstances, etc. There are no perfect solutions. You're doing the full MSc. Module B3 is on multi-core and distributed systems, and we do all of these bits again. You haven't worked it out by now. A1 covers quite a lot of what you do on the whole of the rest of the MSc. A2, 3, B1, B2, B3, fill in the gaps. That's the overall plan. So by the time you get to the end of the day, we'll have done a little bit on distributed systems. We won't have done anything on multi-core because I was told that I would just be asking too much in this module. At some stage, we're going to do a little bit on multi-core in here. Multi-core is good too. Let's go back to our bus design. If we're going to synchronize the messages, if we're going to drive the scheduler on here with tick messages from here, and the duration of a message is of the order of 150 microseconds, give me a significant bad scenario. So I want to send a message to here, a tick message from here to here. What would be a bad thing to happen under those circumstances? If it didn't get it in time, or so I want to talk from here to here. Only one person can talk at a time on the bus, and there's no message preemption on a bus.
Something else might be talking back already.
So if somebody else is talking, at best, and there are message priority levels in here as well, at best, if somebody else is talking and I try and send a tick message, that tick's 150 microseconds late. That's big time late. Once you get to distributed systems, the kind of things we're talking about, saying 1 microsecond, that's bad news, but it's difficult to get to 1 microsecond of jitter. You take it into the distributed world, 200 or 300 microseconds of jitter is easy to get if you just don't take control of these messages. So you need a private data bus here, or to have control over this, or you can't control the timing in this way. So you need to have control over the messages. And what effectively that means is, if you're going to schedule this kind of system, it is a system level schedule you're talking about. It's no longer a question of being able to treat these in isolation, which is still what people try and do. Now, that's a system.
If you were to worry about task scheduling in single processes, we are to worry about message scheduling.
You've got to worry about those. And the two, and the things are very tightly linked. I mean, apart from anything else, suppose you don't worry about that. Suppose you say, okay, that's not my problem. I'm just going to focus on this node, and the guys in the corridor down the road can worry about that one. How do you know then that your task 31 in here, which needs the data from here, is actually going to have the data it needs by the time it's scheduled to run? You can't otherwise. It might be still, that message might be somewhere in the message stack waiting to be sent over unless you have control over these things, because there's not usually much space for error. This might be getting the data. This might be doing your H infinity or PID control algorithm. This might be your actuator node. And that's quite typically a structure of it. So we need the data over here pretty promptly so we can do the calculation, and we need to get the data out again at the other end pretty promptly so we can do the actuation operation. So we can't afford to wait 150 microseconds to get a message through, and it might be 3 or 4 times 150 microseconds if there are 3 or 4 higher priority messages stacked up trying to get through. So we need control over the bus for these parts of the system, and that's sometimes challenging to do. Sometimes organizations who are producing these systems, they are only responsible for one node, and that presents significant challenges because not everybody necessarily who's contributing to that system, who draws up the system schedule. Sometimes that's a bit blurred. There's a worst case scenario. So suppose somebody else is talking, was our error condition here. Suppose this guy is a babbling idiot. What the failure mode is known as. Dublin Airport, a couple of years ago, network node, not an embedded system, standard communication network. One of the nodes on their air traffic control network entered a babbling idiot state. And it just started basically sending out messages on the bus, bang, 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 bang. Took the air traffic control system down. Frighteningly, terrifyingly, it wasn't a failure mode they had even contemplated in the system design. And that really is scary because it was one of the first modes that somebody who comes in from an embedded perspective would look at in these kind of systems. They didn't consider it, nobody died, but the level of disruption that time round, they were fortunate, the level of disruption that time round was enormous over this. So the worst case scenario is somebody disrupts the network by sending out continuous streams of data. It's like a denial of service attack kind of thing on a web-based system. That's the scenario you want to avoid. So we end up having to put in bus guardian nodes if it's going to be high integrity, we don't ever do that. Instead, we put a bus guardian in here. What that bus guardian looks like is that's the master node, that's the bus guardian. We've got one network here. We've got another network coming out of it, and it's this second one at the other side of the bus guardian that communicates with the rest of the bus. The argument is that this is complicated code. All this has to do is it just has to record the schedule. So basically this simply needs to know when this guy is allowed to talk on the bus. And it only effectively opens a connection to the bus at those particular points in the schedule. And otherwise there is no link between that and the bus. And the idea is that that's very simple, easy to reproduce. You can even build it in an FPGA or something, so there was no flexibility about it. And all you would basically set would be this is your time to talk parameter in here. And that's what you would set that up as. But quickly, there become lots more things that can go wrong with these systems if you don't set them up correct. Briefly, one of the ways that you can schedule these systems and the way that many systems are put together is with the controller area network protocol. Simple, low cost, high availability, pretty robust. 1 megabit per second. Data transfer rate. More recent protocols again have about 10 megabits per second. That's a good thing, but they haven't really taken off because the data transfer rates mean that you actually need quite powerful processors to keep up with the data transfers, etc. And that has a cost. CAN remains very, very popular, and this has proved to be fast enough for many applications. You can have up to 32 nodes on the bus. You can actually run this up to 10 kilometers at low data rates, so that's pretty impressive. So you can have a very low speed bus hooking different parts of a very large plant together, and it's all running over CAN. So 40 meters is enough to run it through most vehicles comfortably at high bit rates, and the bit rate gradually drops off over time. The messages are 8 bytes in length. So again, that's rather better than your standard UART. It's enough data for many applications. This is not full-frame video type data transfers. This is not for sending, for broadcasting DVDs to the kids in the back of the car, whatever else. This is a system for doing general data transfers in the system. It's a shared broadcast bus. You can build star networks with it quite happily, but it's basically designed as a shared broadcast bus network. What's neat about this, the fundamental thing that's neat about it is this guy is going to send tick messages. And we want those tick messages to generate interrupts on here. Do we want the tick messages to generate interrupts here on the master node? One interrupt per microcontroller. That guy's got his scheduler triggered by timer overflows. So, and he knows when the messages will arrive. So he can poll the messages generally. So essentially, he sends a tick message on the bus. He knows exactly how long it will take. It can be no closer than 300 microseconds later because of the message lengths that the message will be back. So he knows exactly when he should be looking back in there to check whether he's had a reply. Doesn't need an interrupt here. Maybe this case is more straightforward. When this sends a message, do we want this guy to react to it with an interrupt? No, we definitely don't want that to happen. The only interrupts to be that drive the slave should be from the tick messages that come from the master. So what we want to be able to do is control which messages generate interrupts. Nice thing about CAN is it allows you to do that very, very easily. You can set up which messages generate interrupts on which nodes, and that gives you a lot of flexibility about this. So we can set this up so the tick messages to the slaves generate interrupts, the messages sent back by the slave don't generate other interrupts, etc., etc. This is what the messages look like. There are lots of things like CRC checks, etc., built into this, so it can pick up whether the message has been corrupted or not. if it detects a message has been corrupted, by default, most CAN networks will auto-transmit that message again. Is that good or bad?
Maybe not got time for it to be done again.
If the data is critical for a computation, then yes, we need it.
Almost always bad for us. But we essentially, so if we're going to use this to generate the ticks on here, do we want it to automatically start blasting the things around? We start losing control quite quickly in that. So if you can switch that off, it's helpful. We'll be able to detect that the errors have occurred through our higher level protocols that are running on the system, but it would be useful not to have that automatic. I mean, for example, suppose we've got a dual CAN bus and the message has successfully arrived through the second branch of the system. Maybe we don't care as much that the message hasn't arrived or has been corrupted through one branch. Overall, we probably want control. For 1 millisecond ticks, using about 350 kilobaud is enough. And you can do this with CAN at distances up to about 100 meters. So that's it's an achievable baud rate on a typical CAN bus. This is what the physical layer looks like typically. It's twisted pair cabling. If you've done any work with RS-485, it's just the same cabling that would be used in an RS-485 network. That's not an accident. That's essentially historical, and some of the factory settings can switch over quite easily between an RS-485 traditional network and a CAN bus if they want to do so, running over this. It's differential signaling. What does that mean?
Well, the signal is considered as a difference kind of.
Yep. So why is that good?
You can get more meaning over the two things. If there's any like signal, like radiation or whatever in the cables, it's on both of them, so it cancels out.
So it cancels out. So if you get a blip, electromagnetic interference adds a 10-volt blip on here, the difference will remain the same. So it's essentially pretty robust. It's argued, and sometimes you can on these networks, you can take out one of the cables and it will still work. People argue sometimes this makes it redundant. I think that's absolute rubbish. As soon as you've taken out one of the cables, it's no longer got differential signaling. It's highly sensitive to any levels of electromagnetic interference. That car should be stopped, that plane should be on the ground. It's not redundant, it just happens to be a faintly beneficial side effect, but it's not reliable in those circumstances. If you're going to make it reliable, you probably need two buses. Yeah, okay, so that's just basically saying what happens to differential signaling. There's going to be a latency in the signals. The tick on here cannot possibly be at the same time as the tick on here. The ticks on here and here will, within limits of measurement in most circumstances, be the same. But the tick on here and the tick on here will be different. And the reason is that it depends on the duration of the tick message. So that there's going to be a phase difference in this of about 150 microseconds. If you use any network in these kinds of systems, you need to be aware of what's happening at the lowest level in the system. CAN uses non-return to zero coding. Why on earth do you care? You care because it implies bit stuffing. So at the lowest level, we're not talking the shared clock level, we're not talking the level that we are working with. At the lowest level, if CAN was to send out a long stream of zeros, there comes a point where the clocks in the actual CAN hardware would have drifted enough for it not to be able to pick up. When that eventually goes back to 1 half an hour later, by that stage the clocks will have drifted. What the system does is it uses periodic flips between high and low level to synchronize internally the hardware that's used to actually measure whether that's a 1 or a 0. So obviously that has to be synchronized because it should be checking that in the middle of each bit each time. And to do that, it has to have an internal clock that's synchronized to the message transmissions. That makes sense. So to do that, what the protocol does is, if it's sent if it's sent 5 zeros or 5 ones, it artificially introduces a stuff bit. So it basically artificially, invisible to the user, adds an additional bit to the message and changes the stream from positive to negative. That's fine. Again, why do you care? Why would you care? Synchronization is sorted. Why do I care? So I'm sending a tick message which has data in it between this node and this node. And there's a latency of about 150 microseconds. So I send the message, send the next message, send the next message, etc. And what I want to happen is I say, okay, I can live with the latency, 150 microseconds apart, and we can work out how we can deal with that. What I can't live with are variations. It's 1 microsecond per bit. So if that message is 153 bits long, it's 153 microseconds. If the protocol starts adding stuff bits to the message, we change the timing. And we change it by potentially quite a lot. So if you go through what it does, you've got a possible message variation of 24 microseconds at the maximum baud rate. If you run it at lower baud rates, it's even greater, the variation in the message. That's a lot. That's way at the level where we wouldn't consider to be possible to introduce in many cases in a single processor system. So we've got the possibility that the timing on here is varying by 24 microseconds in tick. We've got a significant level of jitter. If this node is doing our data sampling, well, for a start, which one to use for data sampling? This one. Sometimes people think if it's a control node, this one should be doing the controlling, that one should be doing the data actuation, that one should be doing the data sampling, that one should be doing the control. Because obviously the master node should be doing the control, sometimes the way people think about it. It doesn't work. If that's doing the data sampling, you might have a significant level of jitter in the data sample times. So one possible way of dealing with that is that you manually do software bit stuffing. So if you take control of the parts of the CAN message you've got, you process them yourself, and you effectively ensure that the protocol won't introduce bit stuffing that you cannot control, then you've got better, you can reduce the level of artificially induced stuff bits in the message transfers. And in summary, this is original data recorded from some real application using standard sample data. That got about 8 microseconds of jitter in this particular bus. Using software bit stuffing, that was reduced by a factor of roughly 2 in this application.
Why is the CAN protocol doing the bit stuffing in the first place? Is it for synchronization?
It's for synchronization. It has to do it, because otherwise it would send a long streaming of zeros and ones, and it would lose the ability to detect. It would gradually drift, and it wouldn't be able to detect whether the signals were 1 or 0. It might end up sampling the signals at the point when it was going between high and low if the clock's drifting.
So is the bit stuffing determinacy? Is it fixed at
Yes.
one particular install?
So what the bit stuffing is, it's automatically added by the transmission node and automatically stripped out by the receiving node in CAN. So as far as anything higher up the system is concerned, it's invisible. Why can't you eliminate it completely by artificially doing this? It's because you've only got control of 64 bits in the message. The other bits are set to CRC checks. The other bits are under the control of the CAN hardware, so you can't control those. So that may be enough for you, 5 microseconds of jitter. Suppose it's not.
Do something else.
Yep. So solve it for us.
You've got to use a different program. Like, if you can't actually change any of the rest of them, you can't use can.
You can use can.
Can you disable all the other stuff? Like in the
No.
message?
What's causing the bits? What's causing the jitter? Why is this?
Latency, right?
What is so essentially the jitter is caused by the fact that the different messages will require different amounts of bit stuffing. So how do we ensure that we have a fixed amount of bit stuffing?
No, isn't can supposed to? You said it's deterministic, that it sends the one at the instant time.
Well, what's sent on the bus depends on the message you put in.
So it sees if there are modes.
Yes. Yes. So it's deterministic in that it's a well-defined protocol, but the level of bit stuffing for a particular message that's sent at an instant of time will depend on the message contents.
If you invert the process, basically see how many bit stuffing, how many ones are being sent in, and then
You pad. And you can pad for that, and that's what you do if you do software bit stuffing, but it only lets you do this because you can only do that in the part of the can message that you have control of. Change the protocol a bit. Have the master node just send empty messages. Allow the communicate, basically all of the nodes on the bus can see all of the messages on the bus. So there are different ways of doing the communications. If you want zero jitter, the master needs to send out the same message every time. So you can't have the master sending out different data contents, etc. So what you can do then is just have the master forming the heartbeat of the network, and all of the other data communications happening according to a slightly revised protocol through the slave. But you still have the advantage of doing the shared clock design. Again, it's no perfect solution. This effectively makes this a redundant node that's just doing the timekeeping, and all the processing is then done by these guys.
Wasn't the data sent by master? So if it doesn't send the data, what's the easier to get the data sent? Would we use another slave?
You'd have to, essentially, if you had 3 nodes doing data sampling, control, actuation, we now need 4 nodes. Yep. And this might be an 8-bit microcontroller, because it doesn't have anything to do. So it might be a really very basic microcontroller that's just sending the tick messages. But there isn't another solution, essentially, to that. You can change the protocol, but that's even more expensive, because then you'll have to do a lot of work on that.
Will the problem still exist while the data is being communicated between the slave?
No, because the thing that's driving the scheduler is the messages from here. So it doesn't really matter if there's a little bit of variation in the messages that are, so we've got about 24 microseconds variation in the duration of the messages that are going other way, but we know what the worst case execution time is, so we can handle that. The problem occurs only if the messages from here are driving the timing on here.
So the message running the scheduler should be fixed, and that's why they just had it to be a tick.
Yes. So we're going to have to do a little bit of work on our protocol, but we can make it work in these circumstances. Point of this really is there are solutions to this. The point really is it's a bit like the RTOS things that we're talking about over coffee. You shouldn't be using an RTOS in your system if you don't understand how it works. If you're going to use anything like this in your system, you need to understand the implications of it. So if you have tight timing constraints, you need to be aware of what the network is doing and what it might be doing to that. People tend to assume everything is ideal and don't realize that, in fact, the level of timing variation they're getting from this is potentially quite significant. And even if it's not a shared clock design, even if it's any kind of message passing routine, and you've got 24 microseconds of variation in the message times, that might be significant. Because you can't possibly get better resolution than that on the slave. that's where we're going to end for today. So this is the last of the formal seminars on the module. You'll be relieved to know. What we do today is we give you an exercise to run through. What we'll do tomorrow is we'll run through a case study. So we'll give you slightly less formal exercise to work on in groups. It's not assessed. You may choose not to come. That's up to you. I would urge that you come along, participate in that, because what you learn from that may come up in the exam. So it will not be formally assessed tomorrow. And we run it in that way. What we'll also do tomorrow is begin discussions with all of those of you doing the MSc about project work. And that's what we do on the Friday in most of these sessions. So in future modules, for those of you that are doing the MSc program, we'll ask you to send us an update on your project before you come along. And in the Friday session, I meet with everybody individually and we go through a project update at that stage. Okay, thank you for listening.